Good morning, student. Let's start today's class. Okay, in today's class, we are going to discuss about the efficiency of half-wave rectifier. In previous classes, we have already seen about working function of about what is half-wave rectifier and working function of that rectifier. Okay, how can that half-wave rectify or convert AC to AC into DC. Now discuss about how efficient is that half-wave rectifier. Okay, how efficient is that efficient means how much uh, input AC is converted to output AC. Okay, about 100% or about 50%. Let us see that. Okay, now the the efficiency is the ratio of DC power output to the input AC power is known as rectifier efficiency. That means the rectifier efficiency or efficiency of the rectifier is known as the ratio between the DC power output. Okay, the output which we get from the rectifier is called DC. Okay, so that power or the power of that DC output by input AC power, or that is what we apply or supply as a input in the rectifier circuit, that is AC, and that power. Okay, so efficiency sign eta. Okay, this is eta. Okay, and the it equal to DC power output by input AC power. Okay, now consider a half wave rectifier shown in figure 1. This is half wave rectifier. Okay, here let V equal to Vm sin theta, which is appear across the secondary point. Okay, this is AC supply in the primary wind. Okay, this is transformer. This is primary wind. Okay, this AC supply applied to the primary wind. Okay, and in the secondary wind we get, let's say, V equal to, or voltage of the input signal which you will get from the secondary winding is equal to the Vm sin theta. The voltage is equal to Vm sin theta, because since it is a AC signal, this is in sinusoidal form. Okay, Vm sin theta. Okay, next let Rf and RL be the diode resistance and load resistance respectively. That means PN junction diode has also a resistance. Okay, due to that resistance, in the reverse bias, PN junction diode shows high resistance path. Okay, so in forward bias, that resistance is negligible. Okay, so here we consider that little amount or that small amount of resistance of diode. Okay, which is Rf, and the load resistance which is RL. Okay, this is load resistance, this is diode resistance. Okay, now diode conduct during the positive half cycle, but cannot conduct during negative half cycle. Okay, so this is the input sinusoidal signal, and this is we get in output only positive cycle. Okay, negative cycle is suppressed. Okay, now for calculating the efficiency, we first of all we calculate what is DC power output. Okay, the output current is pulsating direct current. Since this is you see is a pulsating DC. Okay, this is not direct DC. Direct DC, what? This is a smooth. this is direct DC. Okay, this is direct DC, but here the DC is pulsating. Okay, pulsating. So this is called pulsating DC. Okay, and the pulsating DC, the power. Okay, so to find out DC power, average current has to be find out. Okay, due to the pulsating DC, the current is not same for every instant, so we can calculate uh, average current and average current for that pulsating DC. Okay, so calculating the average current, IABG equal to IDC equal to 1 by 2 pi integration 0 to pi IDT. Here, here why can we integrate this much, this little instant? Okay, d phi. Okay, and I. Okay, since this is pulsating. Okay, and we get average uh, current by using integration. Okay, and that after calculating 1 by 2 pi into 0 to pi limitation, and I equal to, we know I equal to V by R. Okay, here V, what happened here, V is Vm sin theta. Okay, so here V is Vm sin theta, and R is, there are two R, Rf and Rl. Okay, there are two R, Rf and Rl. So here I is converted to Vm sin theta by Rf plus Rl. Okay, that means here this is V and this is R. Okay, so this I equal to V by R, we can put here. Okay, then d phi is there. Okay, then Vm by Rf by Rl, this is constant, so it cannot integrate, so we take out from the integration. Okay, and only sin theta is there in integration. Okay, and after integration of that sin theta is equal to minus cos theta, it is the formula. Okay, and limit is 0 to phi. Okay, then we put the value of theta, which is 0 and phi, which is 0 and pi. Here the cos pi. Okay, the cos pi value is minus 1, minus of, since minus cos theta. Okay, so minus of cos pi is minus 1, and minus here here limit, that means here you can apply what, here you can apply the formula, limit formula is cos pi minus of cos pi minus of cos 0 degree. Okay, this is applied here. Okay, and the direct place value. Okay, so cos pi is minus 1, and minus of cos pi is minus of minus 1. Okay, and minus of cos 0, which is minus 1. Okay, so we can get Vm 2 pi Rf plus Rl, here minus 1 plus that is 2. Okay, then Vm by Rf plus Rl multiply by 1 by pi, because 2 and 2 cancel out. Okay, then Im by pi. Im, what? Im, in previously known that Im is V by R, Vm by Rf plus Rl. Okay, so here Vm by Rf plus Rl taking Im, and 1 by pi taking Im by pi. Okay, and DC power, this is what, average, I average. Okay, this is I average or IDC, this is I AVG or IDC. Okay, now calculate power. Okay, power formula is I square R. Okay, power formula is PDC is I square R. So here I is IDC square into R. Okay, R is RM. Okay, that means load resistance. Okay, then um, then what happened? IDC equal to Im by pi. Here Im by pi R square into RL. Okay, this is one equation. Okay, we we get our DC power. Okay, and now calculate what is SC power. The SC power input is given by PSC equal to IRMS square into RF plus RL. Here you see this is IDC, and in SC case we can take that current is IRMS. RMS means root mean square. Okay, we can consider one root mean square value of current in any sinusoidal cases. Okay, so IRMS square is square into RF plus RL. This is the whole resistance. Okay, and for half wave rectifier, IRMS equal to Im by 2. Since the one wave have IRMS equal to Im value or maximum current value, so if for half wave, it the current is half. Okay, so here IRMS equal to Im by 2. Okay, the put that value in the PSC. IRMS square equal to Im by 2 whole square into RF plus RL, which is PSC. We get our PDC and we get our PSC. Now put the in the efficiency formula. Okay, efficiency formula is what? DC power output and SC input power. Put the value of DC power output, which is Im by pi square into RL, and SC input power is Im by 2 whole square into RF plus RL. Okay, now calculate 1 by pi square. Okay, Im is cancelled here, upper and lower Im cancelled. Rest is 1 by pi square into RL, or 1 by 4, which is 1 by 2 the whole square equal to 1 by 4 RF plus RL. Okay, then here 4 is going up, and 1 by pi square, that is total is 0.406 into RL by RF plus RL. Okay, and for 0.406 plus 1 plus RF by RL. Here you see when this RF is negligible, then that RF is negligible as compared to RL. Okay, so that then the efficiency will be maximum. Here the efficiency will be maximum if RF is negligible as compared to RL. That means resistance of the diode. If the resistance of the diode, which is RF, is negligible, then the efficiency negligible as compared to RL. If the, let's say, RL is the resistance RL is 10 ohm. Okay, so in that case the resistance of diode should be 0.0001, which is negligible as compared to 10 ohm. Okay, so when that happened, or that RF is negligible, in that time the efficiency is maximum. Okay, and maximum rectifier efficiency is 40.6%. Okay, remember that the maximum rectifier efficiency of half wave rectifier is 40.6%. Okay, now this shows that in a half wave rectifier a maximum of 40.6% of the AC power is converted into DC power. That means in half wave rectifier, the whole AC input is not rectified. Only 40% of 40.6% of that input power, input AC power is rectified. Okay, so we can lose, or we lose our uh, so much of input. To overcome that problem, we use full wave rectifier. Okay, and that full wave rectifier we will study in coming class. Okay, thank you.